In this lecture, we're going to learn about antennas. In basic antenna theory, you have the transmit antenna and the receive antenna. The hardware will look very similar in that, in many cases, an antenna just consists of a conductor, like a wire, or a system of conductors, or as we'll see, an array of conductors. And for a transmit antenna, the transition occurs from the guided wave of electrical energy to the electromagnetic wave propagating in free space. So that's important to note that you're translating or transitioning between the electrical to the electromagnetic domain. So going through the air out of an antenna is an electromagnetic wave as opposed to just an electrical signal like you have in a circuit. On the receive antenna side, this could be, once again, a single conductor or an array of conductors. The electromagnetic energy that's coming from the communications channel will be converted back or transitioned back into an electrical signal in the form of a voltage or a current. That could, most likely, it's going to be some sort of alternating voltage or current. So what is electromagnetic energy exactly? So it's the accelerating and decelerating of electric charges moving within a conductor. There's an important concept known as reciprocity, which is the interchangeability for transmitting and receiving operations, meaning that, let's say a antenna is in the form of just a wire, right? What's the difference if it's at the receive side or the transmit side? Meaning that that antenna could easily function to radiate electromagnetic energy in the sense of a transmitter, or to actually receive electromagnetic energy. So a lot of times there's that reciprocity concept in a communication system as it relates to antennas. There's also an important concept known as polarization. You may have heard this term with regards to light, a similar type of concept. So this has to do with the orientation of electric fields, and it's the same as the antenna's physical configuration. So the polarization could be horizontal or vertical polarization, and there are other types as well. But it just has to do with its orientation of the electric field. And it has to do with the physical setup of the antenna. So what is a half-wave dipole antenna? So this is an antenna having an electrical length of 1/2 wavelength of the applied frequency. So you have to keep in mind the c being the speed of light equals f times lambda, so frequency times your wavelength, and you would rearrange, lambda equals c over f or vice versa to get the wavelength of your signal at a given frequency. And of course, speed of light being 3 times 10 to the 8th meters per second. So half-wave dipole is good for if you're communicating at frequencies above 2 megahertz. And the impedance ratio, the impedance is the ratio of the voltage applied to the antenna to the current flowing in at any point. So that's a simple kind of Ohm's law. So Z equals V over I in that case. And of course, you have the feeding hertz antenna, so that has to do with frequencies, radians per second. At the center results in the input impedance that is purely resistive. So you end up with an input impedance that is purely resistive, so you get maximum transfer of power. You also have a concept known as resonance, which the resonance occurs when the capacitive reactance equals the inductive reactance, which is a case in which the antenna has a purely resistive impedance, because the XC minus XL kind of zeroing out each other, and then you just are left with a real component. So you once again can get the maximum transfer of power, which is a good thing, because then you don't have any reactive power that gets essentially wasted in your system. So when the antenna is no longer at a half wavelength, you'll end up with a complex term, because again, XC and XL different, so there will be an imaginary term which will make for a complex number. So in this case, you have the impedance being both resistive and reactive, which can complicate things. So half-wave dipole gives you maximum power transfer. The antenna will work as long as there is current flow and the ability to radiate, and the maximum power transfer occurs only takes place when one source or feed line antenna impedances are equal, as I mentioned. Okay, so the radiation pattern is the radiated field strength around the antenna. This is an important concept we'll get a little bit deeper into shortly. Directionality, or whether or not an antenna is directional in nature, just means that more energy will be radiated in certain directions away from the antenna as opposed to others. So lower frequency would be emitted in other directions. A lot of antennas are isotropic in nature. Isotropic means that it radiates equally in all directions, but many directions, like a horn antenna or a Yagi antenna, which we'll talk a little bit about, radiate more in a given direction, so you can get more range, more distance out of that communications signal being transmitted than if it was radiated kind of equally in all directions, kind of like spreading out the peanut butter, if you will, as opposed to kind of putting all of their energy in a given direction. Okay, so the beam width is important too. This has to do with the separation between the half power points, which are the 3 dB down points on the radiation pattern, and the antenna gain has to do with the radiated energy in the preferred direction at the expense of other directions. There, sometimes an antenna gain might be expressed in dBi, which is a little bit of a different than what we've seen with like dBm or dBw. But in a certain direction, you might have like 8 dBi of gain. On another direction, you might only have like 2 dBi of gain or something like that. There's also this other important terminology. So the effective radiated power, ERP, and the EIRP, the effective isotropic radiated power. So ERP is the gain of the antenna multiplied by its power input. So it's just your gain. If your gain is linear as opposed to dB, it will be a multiplicative operation times your whatever your power of your input is. If it's in dB, both the power at the input and the antenna gain, then that would add, right? Because the properties of logs and decibels. So effective isotropic radiated power, so you see that isotropic word, which means it radiates equally in all directions, is the effective power calculations involving antennas with gains expressed in dBi, as I mentioned. And dBi stands for isotropic, as if you were radiating equally in all directions. So that's important to note. And then we have polar plots, which is a cross-sectional view showing three-dimensional radiated power patterns in 2 dimensions. So we'll get a little bit into this, but this is a basic half-wave dipole antenna. So the length of the physical length of the antenna is actually whatever the frequency you're operating at. You would calculate your wavelength over 2, and that's what the optimal length of that antenna would be to get the maximum power transfer. And here's your AC waveform, and your voltage and your current are typically out of phase, obviously. And then here's where Z max occurs, where you have your lambda over 2, and where your impedance on your capacitive side, or your capacitive reactance, equals your inductive reactance, and then you end up with a purely resistive or real component, giving you maximum power transfer. Here is your electric field detaching itself from the antenna. So here's you get your maximum voltage. Here's a dropping voltage. Voltage is at 0 here, and then the charge is building in now in the opposite direction. So this is kind of as your AC waveform, what's happening with the electromagnetic field around your antenna. So radiation patterns. So once again, the beam width is the basically the power between your 3 dB down points here. This is a quarter dipole antenna here, and here's an isotropic point source. So again, radiating equal in all directions. Here's a three-dimensional radiation pattern for a half-wave dipole. So it's kind of showing what's happening around the antenna, you know, in 3 dimensions here. Obviously, you have electromagnetic, you know, patterns. You have an electric field and a magnetic field around the wire. Here's a polar diagram for plotting antenna radiation pattern. So it's like, you know, 0 to 360 and allows you to plot whether or not energy is isotropic, equally in all directions, or whether it's going in certain directions more than others. So for instance, here's a half-wave dipole. You could see the energy is focused, you know, at 0 and toward 180. Those are the lobes of the going out of the antenna here. And that's called your radiation pattern. And that's your elevation. You can also kind of going away from the ground or toward the ground. And azimuth kind of has to do with your, you know, your angle, you know, in the parallel plane relative to the ground that you would basically be aiming your antenna. You know, and this is 0 to 360 degrees as well. Here's a dipole radiation pattern as well. So now we talk a little bit about radiation resistance. So this is the portion of the antenna's input impedance and as a result of power radiated into space. And it varies with the antenna length and the height of the antenna above the ground. So this is your radiation resistance. And an antenna would be constructed of a very thin wire and isolated in space, and the electrical length corresponds closely to its physical length. And by trial and error, you can find the exact length for an optimum antenna performance to give you that maximum transfer of power. Here's radiation resistance versus your height above the ground. So for a horizontal antenna, you can see the radiation resistance increases as the higher you go above the ground here. And then, you know, it basically ends up coming down and kind of basically it's somewhat periodic, but it ends up diminishing down and being attenuated. Here's a vertical antenna. So as you get basically the radiation resistance decreases as you go higher above the ground. And in free space of a half-wave antenna, this is where it falls. So something to keep in mind. Here we have a current feed and a voltage feed for a basically for a generator. So this is a center fed generator at current maximum means it's a current feed, and a generator at voltage maximum means it's voltage fed or voltage feed. And that's called end fed because it falls at the end of the wave, where the end of the current wave, whereas this falls at the maximum current. That's called center fed because basically that's what the current looks like at the generating source. So now we talk a little bit about antenna feed lines. So it's the transfer of energy from the generator to an antenna by a transmission line. So it's an antenna feed line. And the resonant feed line, in the resonant feed line, the transmission line is connected to the center of the antenna. So the transmission line would be connected to the center of the antenna in a resonant feed line. In a non-resonant feed line, there are negligible standing waves if properly terminated in its impedance at the antenna end. And the operation is practically independent of its length. So for non-resonant, it doesn't really depend on the length. For a delta match, when a line does not match the impedance of the antenna, it is necessary to use special impedance matching techniques, and this is a whole art in itself. So a quarter wave match would be to match the low impedance of the antenna to the line of higher impedance. So here's once again, you know, center fed and end fed, just to review. That should make sense in light of what we just covered there. So here's a current feed with a resonant line. So here's your transmission line, and this relates to the length of your basically your electromagnetic wave, and your E field and your I field there. Here are feeding antennas with non-resonant lines, so where it's not as coupled with length. And just here's what's called a delta match, and here's a quarter wave matching transformer, and there's a way you can calculate its characteristic impedance, etc., etc. A monopole antenna, so there are effects of ground reflections that need to be considered a lot of times with antennas. So there's a concept known as multipath, where multiple copies of a reflected transmitted signal will show up at different times of the receiver. That can cause distortion, in the form of intersymbol interference. So that's a whole study unto itself. But basically, monopole antennas. So effects of ground reflection can be used with frequencies below 2 megahertz, and the transmitter is connected between the antenna and the ground, and a quarter wave in physical length or in a half wave operation may be obtained. So basically, you'll see if you really get deep into antenna theory, you talk a lot about quarter wavelength, half wavelength, and we know that half wavelength gives you the optimal power transfer. What about other effects of ground reflection? So counterpoise is when the structure of the wire erected is a short distance above the ground and insulated from the ground. A radiation pattern is omnidirectional, and the loading coil tunes out capacitive appearance of the antenna. So that's for a monopole antenna. So here's what's known as a grounded monopole antenna. So basically the ground is here, so above the ground you have a quarter wavelength worth of length, and then down here you have essentially what we call the image antenna. It's not actually a physical antenna, but you end up getting that effect, and here's kind of what your voltage and current waves look like inside that grounded monopole antenna. And your ground is here. Counterpoise, so this is the top view, so there's the antenna itself, and you end up with these supports, and here's kind of what that would look like. So monopole antenna radiation patterns. So here is essentially quarter wavelength above the ground, and here's what the radiation patterns look like. And then there's relative to quarter and half wavelength. Half-wave dipole antenna and the parasitic element. So the antenna array can be more than one element or component. Basically, an antenna array is when you have more than one element or component to your antenna. And a parasitic array is one or more of the elements are not electrically connected, and it's also termed a reflector because it reflects energy from the driven element. So parasitic, like a parasite, is not a good thing. Then we have a driven array where all elements are connected. And then we have a Yagi-Uda antenna, sometimes just called a Yagi antenna, where the driven elements and two or more parasitic elements are present. All right, so as far as a driven collinear array goes, this is a combination of a half-wave element in which all elements are placed end-to-end to form a straight line. A broadside array is a group of half-wave elements mounted vertically one over the other. And a vertical array is when you have an omnidirectional, remember radiating equal in all directions, in a horizontal plane. So here's an elementary parasitic array. You have the reflector. It's not electrically connected, remember. Then you have half-wave dipole here, and here's your feed. And then with the dipole only, this is what it shows up like. And then with the reflector, you actually get this as well. So that's non-electrically connected. So that's what happens with the parasitic array. A Yagi-Uda antenna, so this is known as a directional antenna because it radiates most of its energy in a given direction. But there is actually a reflector here, so it goes the opposite direction as well. And then these little guys here are called side lobes, which oftentimes are undesirable. But they do exist in practical antennas, so you need to account for them. Here's a 4-element collinear array, so multiple elements connected to form this antenna. That's an antenna type of antenna array. And here's like a half dipole radiation pattern with a collinear array radiation pattern. Here's an 8-element broadside array, just for your reference, just to give you a visual on that. 8-element broadside. And then here's a phase array antenna patterns chart here showing different phase differences in terms of their periods T and their spacing and wavelength. So you'd have to spend a little time with this, but you get the point of basically at different phase differences and periods and wavelength spacing, you get these different types of shapes, which might lend better to certain applications. Sometimes you might be okay with just an omnidirectional. Sometimes you might want to radiate out, say you had like 4 receivers spaced, you might want to radiate out equally at 45-degree angles, for instance, or roughly speaking. In some cases, you might want to radiate out something like this in 2 directions equally. And by the way, if you're into any recording, like microphones use this type of concept as well. So some microphones you can record equally on either side. Sometimes you want to record equally in all directions. Sometimes you might want to record, in more of a narrow area. So it's a similar concept with electromagnetic energy as it is with sound waves in a lot of ways. So let's talk a little bit about some special purpose antennas. So we have a log periodic antenna, which is a special case of a driven array, and it has a wide bandwidth or a broadband antenna. Then you have a small loop antenna in which you have a magnetic field everywhere perpendicular to a loop. There's also a ferrite loop antenna where you have large numbers of loops wound about highly magnetic cores, usually a ferrite core, iron-based, and it increases greatly affected to the effective diameter of the loops. Then you have folded dipole antennas, which has the same radiation pattern as a standard half-wave dipole antenna, but it can actually allow you to have broadband or wide frequency operation. Then you have a slot antenna, which is an ultra-high frequency and microwave frequency operating antenna, and the energy is coupled into a slot by waveguides or coaxial line feeds connected across dimensions of a rectangular slot. So here's a log periodic dipole array, graphically here. So here's your beam direction, and here's your impedance versus your log of your frequency, and you end up with this sinusoidal pattern. So here's your log periodic dipole array. Here you have a loop antenna, so here's your feed line, here's your null, here's your radiation or reception pattern, depending on whether you're transmitting or receiving. And here's a side view of the loop. Here are your dipoles, so this is your folded dipole, in which you fold it around and you have some sort of input impedance here. And then here's your impedance bandwidth for compensated. So you get a compensated version, so you reduce your impedance and you end up with basically capacitor and tank circuit there, or inductor to form your tank circuit. Here's a slot antenna, so this incorporates the waveguides as we mentioned. This is a specific type of antenna that would have to be manufactured. Then we have microwave antennas. So these use optical theory more than standard antenna theory, and they're highly directive and provide a high gain compared to a half wavelength dipole. Microwaves can be divided into bands. There's a table with the microwave frequency designations shown here. So you have L band, S band, C band, X band, KU band, K band, KA band at these various frequencies respectively. So L band is from 1 to 2 gigahertz, ranging to KA band at 27 to 40 gigahertz, which is bordering on millimeter wave types of frequencies. Then we have horn antennas. These are basically add a gradual flare to a waveguide to allow maximum radiation and minimum reflection back into the guide. And these can be circular, pyramidal, and or sectoral in shape. And then you have also parabolic reflector antennas. These are satellite and terrestrial communication systems and have high gain and directivity. So the name from the geometric shape is a paraboloid. So those are some other microwave antennas you might come across are the lens antenna and the patch antenna. So a lens antenna uses the principle of zoning. Savings in bulk and expense justify use of zoned lenses. And then patch antenna is a square or round island of conductor on a dielectric substrate backed by the conducting ground plane. So let's talk a little bit about the link budget and path loss calculations. So many terrestrial communication systems involve point-to-point links where the path of interest is directly between the transmitter and the receiver, both installed at fixed locations. And the terrestrial microwave systems operate with relatively low transmitter powers. Radio transceivers are available that provide very high data rates on unlicensed bands. And the threshold sensitivity of a receiver is the minimum signal level present at the receiver antenna input to produce an acceptable bit error rate. So your bit error rate is based on your signal to noise ratio that shows up at the receiver to tell whether or not you can intelligibly demodulate and decode those bits to recover your transmitted signal, your intelligence. And because microwave communications are line of sight typically, meaning the transmitter and receiver have that direct path between them in terms of they can see each other, a path study must be made to ensure that no obstructions lie anywhere in between the transmitter and receiver, like a building or a forest or a set of trees or something of that nature. And you must ensure that no objects are close enough to produce diffraction effects as well. So here's some examples of horn antennas. So there's a circular, a pyramidal, and a sectoral horn. So picture's worth 1,000 words. You can see the shape right here. And then we also have the location of the focal point for a parabolic reflector. So you probably recall from physics studying lenses and focal points. So that does play into obviously antenna design with parabolic reflectors, etc. There's the depth of the curve, h, and the diameter of the reflector itself. And there's the directrix and the focal point. Here are some microwave dish antennas. You've probably seen these, in people's yards, on people's houses, or around in your travels. So here's your parabolic reflector, your coax cable, your dipole, your reflector, and here's a waveguide. Here's the horn feed, offset feed. So there's some really neat physics behind how these dish antennas operate. So that's a whole study unto itself, but interesting to see here. Here's a polar pattern for a parabolic antenna. So you can see it's very directional in nature with kind of minimal side lobes, but 47.8 dB directional, which is impressive. Here's a zoned lens antenna. So you have your focus transmitter, spherical wavefront, and then beyond a certain distance, it turns into a planar wave. So you'll learn this if you ever take a really in-depth electromagnetic theory class. But this is the introductory type of concept here. And then you have a patch antenna. So you have your dielectric substrate, your microstrip feed point, patch conductor, maximum radiation, coaxial cable feed point, and then your basically half wavelength circular patch diameters, 0.6 wavelength, and your ground plane there. So that's your patch antenna. Here's something called Fresnel zones. So you're transmitting antenna to your receive antenna. Here's an obstruction. Here's your line of sight between transmit and receive. And these are called Fresnel zones. So you have your first Fresnel zone, second Fresnel zone, etc. And you can see this would, this Fresnel zone down here would fall into, be hit by the obstruction, like a mountain or something between the transmit and receive. Here's example path loss calculations. So say your transmit power is 23 dBm. Your transmission line, you get some loss or attenuation, so minus 4 dB. Your 4-foot dish gives you some additional gain, 33 dBi directional. So you end up with an EIRP, basically emitted isotropic radiated power of 52 dBm, which is pretty impressive going out over your channel. But then you have path loss induced in your channels. So you actually end up with negative 75 dBm, but be not alarmed. The dish adds in some additional gains, and then you end up getting some path loss over your transmission line. So received, you actually end up with minus 46.7 dBm. But that's usually enough to recover your signal and demodulate and decode it. So here's your threshold, and then basically if you're above that, then you're fine. So your fade margin was 33.3 dB. So this could have been 33.3 dB worse and still been recovered successfully.